if, right, if you have an answer, you know it's correct, not a problem, shoot me an email, tell me what chapter, what number. I'll go in there and definitely give you the points. Okay, so if you typed in 2 TWO and it meant to type in the number, still a correct answer. So I will give you credit for that. Okay. All right. Let me begin first to go to your site. Okay. Now, here's the front site, the front page of the site. Now, under modules on the far left, as I click, you see that we talk about that every chapter is in its own module. Okay, so scroll all the way down to additional resources. Now, what these are simulations for different things we're going to talk about. We've been talking about the state of matter. Sometimes these simulations assist you in better understanding the subject matter. Let me get one more in. For example, I'm going to take the states of matter and I click it. Okay, so here we have an example of some chunk of matter in the solid phase. You can see the atoms are all close together, organized, very, very crystalline in nature. Okay, and I also may have stated that the atoms are moving even in the solid state. Not until we get absolute zero that movement would stop. But as we put energy into it, keep in mind, these interactions between molecules is what keeps them in the solid phase. The moment we give it a little fire, aka heat, aka energy, we start breaking up those interactions. We're not breaking up the molecules. We're just breaking up the interactions between the molecules. Excuse me, and it may go into more of a liquid phase. Maybe some may shoot off in the gas phase. The longer we heat it, okay, we get to the point where that compound is absorbing that energy, and then we are causing these atoms or molecules to be totally separated from each other and eventually go into the gas phase, okay? Now, so this is a function of energy. We put energy into the system and molecules absorb it, they break up the interaction with other molecules and they separate. Oh, one more. Okay, so when we take the energy away and then back, by icing it, we cool it down. The molecules, the energy level of the molecules decreases. You can see the molecules start to slow down a little bit. Okay, eventually as the temperature drops, and notice here the temperatures in units of K, we'll have more to talk about that down the road, okay, until the point that we have removed all the energy or majority of the energy of the molecules. They reorganize themselves. There's more interaction now between the molecules, and we're back in the gas phase. Nothing happened to the molecules. When we do a physical change, all we're doing is breaking up that interaction between the molecules. Okay? Unlike a chemical process that we'll talk about, where you actually break the molecules themselves and create something new. Okay, so let us go back to where we ended up. And this is where we were talking about what I just demonstrated or showed you was physical changes. Now, with respect to chemical changes, we are totally breaking up atoms, or not atoms, bonds, and we're creating new things, new compounds. Down at the bottom left, a good example, this is an example of your first example of a chemical reaction. We're gonna talk eventually about 6 chemical reactions of all the things that happen in chemistry. The reactions that we normally deal with boil down to 6 different types of reactions. This is the first one. We all know we burn fuel to get that vehicle burning. And notice here they have, let me get one more. We have, okay. We have this general formula, C and H, and then the subscript X. X is a variable, okay, because X can vary depending on the compound. At the minimum, X can be 1 for carbon, and at the minimum, H can be 4. So we call those hydrocarbons because they're made up of nothing but carbon and hydrogen, hence the term hydrocarbon. When we ignite a hydrocarbon, be it gasoline, gasoline is a mixture of different types of hydrocarbons, but they're flammable. This combustion reaction requires oxygen. Now, for us here at Chem 130, there's a variety of different products that are made when you combust hydrocarbon. But for us, when you burn or combust a hydrocarbon, the only two products that we're going to worry about that are being made are carbon dioxide and H2O, otherwise known as water. Okay, so that is a chemical change. You can notice that the hydrocarbon was completely broken up from the CXHX to create carbon dioxide and water. Typical type of chemical reaction. So, so how do we know that something happened reaction-wise? Most of these are based on observations. There's a variety of different methods, instrumentation methods to tell as chemical reactions occur. But in general, anything that burns, cooking, cooking's a chemical reaction. Any type of metal, you can see you got rust. I had an old truck, had a lot of chemical reaction occurring on it, rust. Those are examples of an example of some type of reaction. Sometimes you may react A and B together, put them together, and bubbles are emitted. But there's not a lot of heat coming out with it, but you got bubbles emitted. That's a good indication you may have a reaction. A good example of that would be alka-seltzer. The moment you dump it in water, it breaks apart. Carbonate breaks apart. One of the products is carbon dioxide, and hence it's bubbling on you. Okay? Sometimes you put two reactants that are pure liquids. You put them together, and you get a solid. You get what we call a precipitation of some compound, or a precipitation reaction. Formation of a solid, good indication of a reaction. You could release heat. You go to the pharmacy, you buy yourself one of these heat packs, you take the pack, you smack it, the chemicals in there react. Guess what? That pack, it's hot, okay? Some type of chemical process occurred because one of the products it's making is heat, okay? Or the counter to that is a cold pack. Same place, go to the pharmacy, buy a cold pack, smack them. That little pack gets cold, so you can use it on your body for whatever reason. Glow sticks, chemical reaction. When you crack that glow stick and let it react, you'll see light being given off. Again, good indication of reactions occurring. Fireflies do that all the time. Good reaction process. You may get a color change, okay? It goes from clear solutions to a blue to a yellow or some type. That's a good indication. Or you may get some type of an odor. Good example of something that gives you an odor are a lot of like wintergreen mints. You put them in your mouth, they taste pretty good. Those things are made up of alcohols and what we call acids, carboxylic acids. By themselves, they're kind of nasty smelling. But when you put them together to form this new compound called esters, they smell pretty good, all right? The opposite of that, you get a lot of chemicals that don't smell so good. So those are type of indicators that you have some type of chemical change that has occurred. Now, here's an example of a reaction, and it's written out. We're going to get to the point where we're going to get a paragraph like this written out, and then you're going to be asked to write the reaction based on the words, okay? So here we look at It's telling you there's a chemical reaction between sodium metal, and they give you the symbol for sodium, and in parentheses S because it's a solid, and chlorine gas. Now notice there's a subscript on that Cl. It's chlorine gas. There's 7 elements that are what we call diatomic. A few more slides down the road, we're going to talk more about that. But it's a gas. It's a poisonous gas, very hazardous. Sodium itself is a very reactive metal. If you dump it in water, it will react violently with water to create hydrogen gas and blow up, ignite. So we got a hazardous reactive metal, a poisonous gas, and when they react together, they produce something that we all put on our French fries or whatever, sodium chloride, which is a salt. Totally different chemical, totally different formula, okay? So that is an actual chemical reaction. Here we have pictures of that reaction. We got a picture of sodium on the far left, typical metal, kind of shiny a little bit, but pure sodium is kind of soft. You can cut into that very easily. Here we got chlorine and then sodium chloride. Note something interesting here because we're going to do a lot of that there are some numbers here to look at. Now, the subscript 2 on chlorine, which I've highlighted, that indicates how many chlorine atoms are put together. We never change that. It's etched in stone, okay? Now, the other 2, which is much larger 2, we call that a coefficient. It is placed in front of the symbol. That tells us that we need 2 atoms of sodium, okay? And if you look at the far end, as a product, we got a 2 in front of sodium chloride. That tells us that we made 2 molecules of sodium chloride. We have to balance the reaction. Why? Because conservation of matter and conservation of energy tells us, you know, if I start off with 1,000 sodium atoms in the beginning of the reaction, I will end up with 1,000 sodiums at the end of the reaction, going from the beginning to the end. Okay, that's a conservation of matter. So we put these numbers in front to balance the chemical reaction. It also tells us something else that I mentioned early in the introduction about stoichiometry. Remember that word stoichiometry? And I used the example of a bicycle and tires, where you need 2 tires per bicycle frame, talking about a 2-wheeler. So there's that ratio of 2 to 1. Here we have a ratio of 2 sodiums per 1 chlorine atom. And we need that ratio because eventually we're going to use that ratio to do some calculations. If we ever need to calculate how much, if we need to calculate how much sodium do I need if I need to make 10,000 grams of sodium chloride, we're going to utilize that ratio to determine that. Okay. So we have to learn, we will learn about balancing chemical reactions. All right, so.
Mr. Dort.
Speaking.
Sorry, I don't know if that's how you say your last name. Really quick, so going back to the chlorine, the 2 in between the Cl and the G, you said that's the number of atoms that you put in?
That's the number of chlorine atoms put together, okay? And let me draw it a different way, okay? If I were to redraw that, I could say Cl and put a hyphen there, and that hyphen represents a bond between the 2 chlorine atoms, okay? Now, instead of writing it that way, since there's 2 atoms, we can just do a subscript, okay? That makes sense? Another example would be H subscript. H subscript 2 for hydrogen. That hyphen represents a bond between the 2 hydrogens. Okay? All right. Oh, somebody needs to be muted. picking up some sound. All right, so let's go to the next step here. Let's cancel, release some of this. Now, can somebody has their mute? Can you mute yourself? All right, who needs to be muted?
Amber Live.
Amber Live? Okay, here it is. There we go. We're good now. Okay, so here we have 5 equations, 5 chemical equations, okay? Now, I understand at this point in time, we don't really know what each thing means, okay? So we're gonna do an analysis. We're gonna look at what we're given, and we're gonna try to figure out, just based on what we're observing and deduce, what is happening. Is it a physical change, or is it a chemical change? Bear in mind, a physical change does not change the formula. A chemical change does change the formula and generally results in making at least a minimum 2 different new compounds. All right, so we look at the first one here. Oh. And we have something that's written as NH3. We're going to use this guy quite a bit throughout the semester. NH3 FYI is the formula for ammonia, okay? Now, remember the arrow represents some type of process, chemical or physical. But if we look at NH3 as a reactant and we go over to the product side, guess what? It's the same. Nothing has changed. The only thing that has changed is that we go from a gas to the liquid. Remember, the parentheses, are those letters in the parentheses represent the state of the material. G for gas, L for liquid, S for solid. So what that states here is that this process must be a physical change. Okay? Second example. Again, we start off with NH3, ammonia. Okay, you may not know what that is, but that's okay. You know it's NH3. But guess what? We got a plus here in the reactant side. That should flag to you that I must have this. It's got to be a chemical change. Why? Because I'm creating at the minimum 2 new products, and that's what happened. I made N2, okay, and H2. It created nitrogen and hydrogen, both of them gases. That would indicate that this example is a chemical change. Okay? Now take a look at this number 3. Looks very similar to H2O or water, right? But it's really H2O2. Okay, it's got an extra oxygen. That, FYI, is the formula for hydrogen peroxide. Use it to color your hair or use it to be treating cuts. Okay? And it's in a liquid form. Reaction proceeds. Again, we find a plus on the reactant side. That should indicate to you, I got a reaction occurring. And here it actually made hydrogen and oxygen. Okay? Notice the subscripts on hydrogen, notice the subscripts on oxygen, and then nitrogen. Again, that means there's 2 of those atoms bonded together. We call those guys diatomic. Di because there's 2 atoms, the same atoms bonded together. There's 118 elements. There's only 7 of them that are diatomic. We're going to get to that here in a few slides down the road. Now, the next one, again, we continue with H2O2, okay? We look at the product, and it remains the same structurally. H2O2. All right? So that would suggest, what would that suggest? Somebody's in the loop. Somebody's in the loop. Okay. All right. Let me check here.
I have a question.
Sure, go ahead.
For the third one,
Yes.
even obviously I understand why it's a chemical reaction, but
Okay.
the fact that it changed from a liquid to a gas, can't it be both a physical and a chemical change?
No, and I'll tell you why. Because for number 3, it made 2 different products.
Okay.
Okay. All right. It took H2O2 as a reactant and totally broke it apart to its elements of hydrogen and oxygen.
Okay.
Okay. And hydrogen, by nature, being here on Earth, is a gas. And so is oxygen. Okay. Okay. Did that answer your question?
Yeah.
Okay. And if we look at number 4, now here, you start off with H2O2 and you end up with H2O2. Again, no chemical change whatsoever. It's a physical process because it went from a liquid and it went to a solid. Okay. Now, finally, the last one, C6H6. You guys remember what general name we call those guys? Now, remember the Lamborghini slide? No, hydrocarbons. Okay. Hydrocarbons are made up of nothing but hydrogen and carbon. In the previous slide, I had an X down here because I said that X is a variable. In this case, there's 6 carbons and 6 hydrogens. Right. So C6H6, something happens to it, we end up with C6H6, but it's in a gas phase. So it went from a liquid to a gas. What do we call that normally? Anybody have an idea? Going from a liquid to a gas.
Physical change.
Yeah. Isn't there a specific name of that
Boiling.
process?
Oh, okay.
Boiling. There you go. Thank you. We're boiling. So all I did was boil, and so there's a physical change. Okay. So to take away from these type of reactions that you see, yes, we know that you're not familiar with how they're put together and structurally, but just analyze it. See, NH3 in the beginning for number 1, I got the same thing at the end, NH3. That should indicate to you physical change. Anytime I break the reactant into making 2 different products at the minimum, 2 different products, I have a chemical process. All right, let me clear this. All right, so let's jump into elements, compounds, mixtures. A lot of it's pretty self-explanatory. Now, if you haven't done so, where are we at? You share? This is the periodic table that we utilize in Chem 130, okay? Now, it is a little bit dated because there's 118 elements. If you look at the bottom right corner, at this point, they have very generic letters, UV, but they all since have now been named. They all have their own names. The last 3 were found about 3 years ago or so. So there's 118 elements. Also, the takeaway is there's a little stair step here. Keep an eye on that, okay? Now, this last column, well, on top of each column, let me mark it. you will find Roman numerals. Now, I learned last semester and the previous semester that I guess Roman numerals are not very common anymore unless you're doing the Super Bowl. Okay. But in Roman numerals, capital I is 1, and V is 5, and X is 10. Anyway, Roman numeral 1A, that's column 1, and then column 2, the next one here. Then shooting across, we got column 3A. And then when you put an I in front of V, that means to subtract 1 from 5, so there's column 4. And there's column 5 for V. And if you put the I after V, now it becomes 5 plus 1, which is 6. And if you put 2 I's, you got column 7 and finally column 8. That number 8 is a very magical number. We're going to be using that a lot. Now, this periodic table is going to give us a lot more information. If you look down the bottom, we have most common polyatomic ions, solubility rules, and then what we call activity series. All this information we're going to be utilizing, okay? Now, this last column, column 8A, all those guys are gases, every one of them, and they're called noble gases. Noble because they're unreactive. Unreactive because they have 8 electrons around this outermost orbital. But I don't want to jump too ahead of myself right now. Okay, so please print this out. Be familiar with it. I keep one here all the time to make reference to it. Use it quite a bit. Yeah. And the other one was the shapes table. We'll be using that also, but not right away. Let me go back to where we were. Okay, so the elements, 118 of them. Well, that's only one type of atom, okay? You can't break them down any further. If you do, now you start breaking them down into the subatomic particles, which are the protons, the neutrons, and the electrons. And I did mention that those guys are even broken down even further down, but we're going to stick just the protons, electrons, and neutrons. So when you're at that level, you have an element. A compound is defined as any chemical that has at the minimum 2 different atoms, okay? Hence, for example, sodium chloride, okay? Sodium chloride has sodium and chloride. That's a compound. Hydrogen gas is only H2. We have hydrogen and hydrogen. They're the same element. It's still an element, even though there's 2 of them. But they have to be different to be classified as a compound, okay? As far as the atoms are concerned, that are bonded together. All right, in fact, from the compound, if we break them down further, then we just break them back down to the element. Now, obviously, this is self-explanatory, pure, all particles that are same, there's nothing else in there, so on and so forth. Okay, now, of course, we can have mixtures. Okay, mixtures of, in this case here, we can have a mixture of elements or a mixture of compounds, any combination thereof. Okay, so take away from this flow chart is basically the diagrams. We utilize a lot of diagrams for you to analyze and come back with some type of answer. If we start, let's look at the far left, okay? You can see there within that circle, we have these orange colored round objects, okay? They're all the same color. There's nothing else in there. So one can conclude that what we have here are simply atoms of the elements. That's it. If we go across to the next one, we can look and see that it looks like 2 of them are bonded together. And they are. They're represented as 2 atoms that are bonded together. There's nothing else in there. That is a good example of a diatomic element like hydrogen and oxygen and so forth. It's still an element, but we call them molecules because there's two of them. Okay. Now we go over here, we can take a look at Mickey Mouse right there. Okay, doesn't it look like Mickey Mouse? Okay, got the ears and everything. Two different elements. The yellow little spheres represent some type of atom. And there's two of them, and then they're bonded to the central atom. We're always going to have a central atom, and everything else is bonded to that. Okay? It can be more complicated than that, but that's beyond the scope of 130. But for us, there's always going to be one central atom, and then everything else is bonded around it. And you'll always be told who the central atom is. So this could represent water, H2O, where the yellow spheres represent hydrogen. And then the red ones represent oxygen. And then going across, we're going here, we can see, okay, we got two different colored atoms which tell you compound. So we got like a green and a lighter green bonded together, okay? So it's not diatomic because they're just together in two different colors. All right, and we call those compounds. And we go across and we talk about mixtures. Huh? Definitely we have a mixture here. We got some dark colored spheres. Okay, we've got four of them. And then it looks like we have some diatomic elements. So we got a mixture of an atom and a diatomic element, or molecules of a diatomic species. And then finally, we still have a mixture here of three different things, all of them atoms. Okay, so there. So what kind of examples can we think of as mixtures? Well, metal alloys are mixtures. That gold that you have on your ring, your watch, your earrings, whatever you're wearing that's gold, it's not pure gold. Okay, pure gold by itself is extremely soft, and it wouldn't function well as a ring the moment you got your hand smashed or your finger smashed. So they put other elements in there to give it strength. For example, steel, the steel we use to build buildings, it's not pure iron. Steel is nothing more than iron, but we add things like carbon and other things to give it strength. Okay, brass is a mixture of copper and zinc. Tap water, big time mixture, because that tap water is loaded with tons of ions, tons of organic pollutants, all kinds of things in there. And the air around us obviously is a good example of a mixture. Yeah. Now, something that's pure, if we were able to get sodium chloride and clean it up very well, we can think of sodium chloride or salt. Now, the term salt, for the non-chemists, when we think of salt, we think of sodium chloride. But in chemistry, a salt is a multiple different types of compounds. When you look at sodium and you look at chloride, you have two different elements. It's a compound. But instead of sodium chloride, I could have said potassium chloride. That is also salt, okay? So it's not limited, the term is not limited solely to sodium chloride. A diamond, pure diamond, very rare, that's pure. Now, think about this for a second. Carbon, a pure diamond is made up of nothing but carbon, okay? Yet the diamond is one of the hardest things on earth. You go to a hardware store and you buy some graphite. Guess what? That's made of carbon too. So, you know, here we go. I got a diamond over here made of carbon. I got graphite, which is a dry lubricant made of carbon. Wait a minute, why one is the hardest thing in the earth and the other thing is pretty slimy? Okay, well, it has to do with the way the atoms of carbons are put together in diamond relative to each other. That has a big effect on the overall properties of the diamond compared to graphite, the way the carbons are put together, they're more in sheets and therefore very slimy and is a good dry lubricant. So, I mean, we're all familiar with styrofoam. Styrofoam is made up of nothing but carbon and hydrogen, okay? Low weight carbon and hydrogen. But I can make styrofoam or polystyrene such that by changing the formula a little bit, I can make material that I can build buildings with. You know, and all of it is due to the way the molecules are put together relative to each other. Okay, so the still water is a pure material. 99.99%, nothing's 100%. In that pure water you buy in the grocery store, it's fairly pure. It's difficult to get 100% pure material, but for our purposes, okay. A lot of the water that's sold out there, they use the still water, then they come back and they add magnesium chloride and salt. And so I'm like, save some money, buy a bottle of distilled water, a couple of tablets of magnesium chloride and salt, and you got smart water. Remember that smart water container? They make distilled water and then they add salts back in. Okay. Diagrams, very important because we use a lot of them. And from these diagrams, you know, it's not mentioning any type of specific compound, but be able to analyze them. Do we see an element here to the far left? In fact, even characterize even further, it's a diatomic element. Okay, the one in the middle, we got the white sphere is the central atom, and then the dark gray ones are bonded to the central atom. Two different elements, hence we got a compound. And then finally at the last one, obviously you can see you have a mixture of compounds and at least two different elements, okay? So number A would be an example of an element. B, where you can see here, we got a dark central atom and then three lighter color ones around it. That's a compound, two different elements, I should say. C looks like we got a mixture of elements, okay? D looks like it's pure element itself. And then E, again, the way it's drawn here, compound. There's nothing else in there. F, you can hopefully pick out that you have a mixture of a diatomic element and two different compounds. And then finally G, again, we got a mixture of an element and a compound, okay? And then finally H, simply a element. And the way it's drawn, very structured, very ordered, I could deduce that it must be a solid, the way it's written. Okay, but let's talk about the elements. Okay, every element has a unique name, symbol, and number. Okay, let's go back to the periodic table for a second. Okay, you can see here, there's the symbol, the letter, and the number. Here, the number's on top. And that number goes from 1 to 118, okay? Every element has a number. And that number represents some information for you. In fact, I'll tell you now. That number represents how many protons. The atoms are made up of three components, as I mentioned: protons, neutrons, and electrons. The protons and the neutrons are in the center of the atom with the electrons orbiting around. That number tells you the number of protons, which defines the element. So number 20 is calcium. If I take a proton out, I make number 19, which is potassium. Totally different element, okay? And we'll get back to that part and work with it quite a bit, okay? Now, when we write the symbol for the element, if it's a single letter, the letter is presented as a capital. So carbon is capital C, not lowercase c, because that doesn't represent carbon. It's uppercase, hydrogen, H, okay? If there's a second letter for the symbol of the element, that letter must be in lowercase. First letter uppercase, second letter lowercase. Now, why is that important? Because if you were to write it in uppercase, like you see here, CO, what you in effect have done is wrote some other compound. That is the formula for carbon monoxide, which is totally different, obviously, from cobalt, okay? So lowercase and uppercase is important with respect to writing the symbol out. Now, most symbols have the English names like H for hydrogen, oxygen, helium, etc. If I happen to go over the time or get close to time, please remind me. I get kind of get going here. I forget, I lose track of time. All right, some of them have Latin names. Like lead has the symbol PB from plumbum, which is Latin for waterworks, okay? And OUAU is a symbol for gold, which means golden dawn. Now, be familiar with the first 20, okay? The first 20, let's go back. And we can do that real quick. So number 1 is hydrogen, okay? And then I shoot across to helium, which is number 2. Number 3, Li is lithium. Next one is beryllium. Now number 5, which is boron. 6 is carbon, nitrogen, oxygen, fluorine, and then Ne is neon. And then we wrap around the corner. We go to number 11, which is sodium. The symbol for sodium is Na, which comes from the word natrium. Mg is magnesium. Then we shoot across to number 13, which is Al, good old Al, which is aluminum. Si is very important element. Your computer or electronic device wouldn't function very well. That's silicon. Next to that, P is phosphorus, S is sulfur, Cl is chlorine, not to be mistaken with chloride. Chlorine, I-N-E, is the element. Chloride, I-D-E, is the compound, okay? And then 18 is argon, and then we go around the horn again to number 19 for K, which is potassium, and then we end up with number 20, Ca for calcium, okay? Very important ion for bone, excuse me. All right, so those are the first 20 elements. Be familiar with these also. Ag is silver, Au is gold, Pb is lead, as you mentioned. Then we have Br is bromine, I is iodine, and then the last one is Hg for mercury, okay? Notice for bromine and iodine, I said bromine, INE, I said iodine, INE, like I said chlorine, INE, and the last one is fluorine, INE. Those are the elements of INE. They will eventually become IDE, like stannous fluoride you use to brush your teeth with. You're not brushing your teeth with fluorine, but with fluoride. And you're not putting chlorine on your French fries. You're putting chloride on your French fries. Okay? Now, when we
Quick
talk
question.
about... Sure. Go ahead.
On the last page under bromine, I thought all the elements were supposed to be lowercase. Is that just a typo, or is there a special reason why it's uppercase?
We're under bromine?
Yeah.
Oh, no. The symbols. This bromine, the name is either lower or uppercase. Is that what you're asking?
Uh, well, under the notes, it said note that all element names are lowercase.
Okay.
And that's why I just saw that it was uppercase. I didn't know if there was a special reason for that.
No, that's a typo there. A
Okay,
typo
gotcha.
for that bromine. And, but when we're talking about the symbol, that first letter is always uppercase and the second letter is lowercase.
All right, cool.
Okay, all right. All right, good question. All right, so now let's talk about the physical states of the elements, okay? You got 118 elements. You got to memorize them all, right? No, not at all. First of all, when we talk about the physical states, we have to specify and qualify it by stating that we are at 25 degrees Celsius, which is roughly room temperature, and that we are 1 atmosphere of pressure. Here right now in Arizona, we're about 1 atmosphere of pressure. Colorado, up in the mountains, no, you're less, okay? 20 feet in the ocean, a lot more pressure, okay? So, but here's 1 atmosphere. Why do we qualify that? Well, because the physical properties change with temperature. What we learn here maybe will not be true on the surface of the moon or on the surface of the sun, okay? So for 25 degrees, 1 atmosphere, this is the true statement, okay? Number 1, mercury and bromine are liquids. There's 118 elements. Only 2 elements are liquids at 25 degrees, okay? Now, H2, N2, O2, F2, and Cl2, hydrogen, nitrogen, oxygen, fluorine, and chlorine are gases. Now, we introduced something new here called noble gases. What is that? Remember that on your periodic table, group, where we go. Group 8. Uh-oh. Starting from here all the way up here, Roman numeral 8, that is the noble gases. Notice how many horizontal rows we have. 1, 2, 3, 4, 5, 6, 7. Keep that number in mind. If they ever discover or put together element number 119, you're going to go around over here and it's going to pop out in row number 8. Okay. Anyway, so we have 7 noble gases, and the reason they're called noble gases is related to that Roman number 8, is related to the number of electrons. They're noble because they're unreactive. Okay. They're pretty much inert. All right, so those 7 and hydrogen, nitrogen, oxygen, fluorine, chlorine. So we got 7, 8, 9, 10, 11, 12. 12 elements are gases, okay? 2 are liquids. That means all the other elements are solids at 25 degrees and at 1 atmosphere. Okay. This here.
Mr. Duarte?
Yes, speaking. Go ahead.
Someone is requesting that you repeat yourself one more time. Why are they known as noble gases?
Oh, okay. Sorry about that, Rosabella. I didn't catch. Yeah, good catch here. Sometimes I miss the chats. The question is, why are they called noble gases? They're noble gases because we're going to learn about this in the next chapter. Is earlier I stated the model for the atom is we have in the nucleus we have the proton and the neutron, and orbiting around the nucleus are the electrons. Okay. Now, when with the exception of helium, when the driving force in nature is to have 8 electrons orbiting around the whole element. And when they have 8 electrons, they can't put in number 9 because these electrons are in specific orbits. And if you had 9 electrons, it needs to go up another orbit. So from an energy perspective, that, you know, nature's lazy. It's not going to use more energy than necessary. And so they're noble because their outermost shell is full and they will not react anymore. Keep in mind, chemical reactions are nothing more than electrons either coming in to one element or going away from another element. It's just the transfer and the sharing of electrons. That's where all the action is. This is all the chemical reactions. The nucleus very rarely do anything. It's these crazy electrons that cause things to react. Okay, so I hope that answered your question. All right.
It did.
So, okay, good. Now, if we look at this table, you can see here that we have kind of at a glance, you can see the 2 liquids, which is mercury and bromine. Okay. The gases are in yellow. Hydrogen's way over here, and it's there for a reason. We're going to learn why hydrogen's in group 1A. Okay. And then everything else, yellow, are gases at 25 degrees and 1 atmosphere. So everything in, I guess, light blue coming from my end looks like a light blue. Everything else is solid. So if you got your reference points and if you're said, and they said, okay, number 38, is it a liquid, solid, or gas? Boom, just go to 38, find your reference points where everything else is a gas or a liquid or wherever. You should be able to define what physical state it is. Okay? All right. All right. Remember earlier I said diatomics. Those are elements that at 25 degrees do not exist by themselves. From an energy perspective, it's not energy favored. So what they do is they combine themselves with another element of the same atom. And so we have 7 that are called diatomic. This helps you out. Have no fear of ice cold beverage, if you like, where the H represents hydrogen, the N represents nitrogen, F represents fluorine, O for oxygen, I for iodine, C for chlorine, not carbon, okay, don't get that confused, and B for bromine. So 118 elements, 7 are diatomic elements at 25 degrees and 1 atmosphere. Now, we got 118 elements. They're classified even further. 3 ways only. You're either a metal or you're a non-metal or a semi-metal. Okay, or metalloid is another term you may find someplace. Now, anybody know how I can make a mule? Where does the mule come from? Don't say the mule store. Okay. No. Well, a mule is a combination of a donkey and a horse. Okay? Donkey and a horse. That's what semi-metals are. They are the combination of a metal and a non-metal. They have some metal properties and some non-metal properties. Okay? Now we're gonna use the next one. Okay, two different colors. All the nonmetals from my end look like I don't know, reddish, light reddish color. Okay, but let me talk about the metalloids first. Okay, because if I start with bromine here, number 5, and I go diagonally, I end up with silicon. Silicon is a very important metalloid. Your electronic device wouldn't work without it. Okay. Silicon, now if I go straight down from silicon to number 32, That's another metalloid. I make a right turn 90 degrees to number 33. Here's the other one. So I go down again, and then across again, and then down again, and then across again. And yes, and 117 is also a metalloid. Okay, so I'll go diagonally, down, right, down, right, down, right. Okay, those are metalloids. Everything to the left of that group are metals. Okay, everything to the right of that group are nonmetals, but don't forget hydrogen. Hydrogen is a nonmetal.
I have
Okay.
a question.
Sure, go ahead.
And I don't know if it's just how I'm looking at it, but why is 117 the last at the bottom? It says it's a you said it's a metal, right? Or not? Or
A metalloid.
yeah. Why is it a different color than the rest of them?
Oh, it has not been updated. This is updated. It's white. You know, the
Okay.
letters you see the letters there in number 115, 117, and 118, they have just letters U, UP. Okay, because at the publication time of this periodic table, they did not update it with the new names.
Okay.
We're trying to get this updated, so don't let that confuse you.
Okay.
They all officially have names now.
All right. Thank you.
Okay, yeah, no problem. Let me see it now. Okay,
A question
So-
before you go on.
sure.
So you said to the left, it's non-metal?
Yes, correct. The ones in blue color, light blue color, are metals. To the right, the ones in like a light red color, see them? Everybody here, you know what? Let me change the color here. Okay, so here, everything in there's, I'm trying to highlight all the non-metals. Okay, you see, and from your end, do you guys see a different, like a light pink color?
It looked like pink. It really be like.
Yeah, light pink. Everything in light pink is a non-metal. Everything in light blue is a metal. Okay, just like it tells you up here in the, right here, yellow for semi-metals, pink for non-metals, and blue for metals. Okay. Now, why is this important? Because of all the compounds that we have, there's only two types of compounds. There are types that combine, a metal and a non-metal combine to make one type of compound. But the other type is a combination of non-metals. For example, carbon dioxide. It's a combination of carbon and oxygen, two non-metals. Sodium chloride. Sodium's way over here. Chloride's way over here, number 17. You got a metal and a non-metal. That makes a whole new different type of compound. Someone had a question? Oh, meal? Yeah, maybe you're hungry, Jason. Okay, and so at a glance, you should hopefully just be able to look at this, find your reference points, and determine, okay, number 35, is it a metal, non-metal, metalloid? Okay? Because later on, we're going to be looking at compounds, we're going to look at formulas, and you're going to need to determine whether it's one of those two compounds I said, a combination of a metal, non-metal, or a combination of two non-metals, because that tells us totally different properties and things how those compounds react. All right, so let's clear that up. Got a big mess there. We're almost done. Okay, so properties of metals, they tend to be shiny. You can smack them, you can pull them out, stretch them out. That's a general trend. All of them are solids except mercury. And they have a very high density. You know, density is that ratio of mass per volume that we talked about last time. They tend to have a high melting point, okay, to get them to melt. And they're very good conductors of heat and, of course, electricity. all the wiring in your home made up of metals. With respect to nonmetals, when they're solids, they tend to have a dull appearance. And if they're solids, they're brittle. Majority of them are gases, and their density tends to be very light. Okay? And they tend to melt at relatively low melting points. And they're not good conductors of electricity, hence they're good insulators. Where metals are good conductors of electricity and terrible insulators. All right, so from the periodic table, yes.
Just a quick clarification. For a semi-metal, it's the combination of both the metal properties and the non-metal properties, right?
That's correct. They have properties of a metal and a non-metal, just like a mule.
Okay.
Okay? Did that answer it?
Yes.
Okay, good. All right, and then, okay, so looking at the periodic table, at least for the first 20 and the ones that gave, you'll be able to name those elements, okay? Looking at the periodic table, but remember you have the periodic table be able to determine, okay, who's a solid, who's a liquid, who's a gas, you know, and say, okay, number 45. Okay, you may not know who 45 is, but you know where it's at in the periodic table. Is it a solid, liquid, or gas? Things of that nature. Okay. Looking at that stair step, there's a little stair step on the periodic table. That's your reference point. Okay, to tell you that's where the metalloids lie. So from that point, be able to determine what element is a metal, which is a non-metal, and which is a semi-metal or metalloid. Okay. And again, have no fear of ice cold beverage. Which ones are diatomic? Okay. Down the road, you might get, like we did earlier, sodium. You might get a paragraph of a chemical reaction, and reading the paragraph, you need to be able to convert it to formulas. So we know that when it says sodium reacting with chlorine, given that chlorine is the element, then knowing that chlorine is diatomic, we would need to write that as Cl2, okay? With that, we're done. Okay, congratulations, you made your first week. Wasn't too bad, was it? Okay, 15 more to go. All right, are there any questions? You can do it, exactly. Yeah, keep up. A lot of you have done your activities. I wait till the due date so I can grade them all one time. So I will get them graded ASAP. You know, keep up with the homework and activities. I think that's coming up. Homework number 1. Next Tuesday, I'll start with chapter 2 and maybe a little bit of 3. Okay. So any questions, comments, concerns? No? You guys stay safe out there, and we'll see you on Tuesday. All right? Feel free.
Thank you, sir.
Thank you. Feel free to come to my SEC class. I'm starting from scratch, point number 1, where you did on Tuesday. So same stuff. So if you need more torture, come on down. It's from 1 to 3.
Thank you, sir.
All right. Thank you. Take care.
Thank you. Have a good one.
You too.